So let me get started. Of course, you have an exam on Thursday, chapters 26 through 28. And then all your web assignment will be done by then. Really the only thing that you're going to have to do, unfortunately, during the break is the DC Circuit Lab. I'm not going to start anything new today. Okay, I'm not going to start anything new until after the break. So I just want to do RC circuits, and if I have time left, I have some questions to ask you. In fact, I'll create a poll, and then I have a bunch of multiple choice questions you can try answering. Okay, so that'll be my goal for today. So I'm going to try to do RC circuits, and then have some time to have you guys answer some questions, just to test yourselves. Okay. So anyway, let me get started, and then if you have questions on the exam or whatever, please just ask them at the end of class. I should be able to finish this a little bit early. I hope I'm not wrong. I will say the exam will have 4 questions on it, okay? There'll be 4 problems. They have multiple parts. And I'm really hoping that, I'm fully expecting that the average will be higher on this test than the previous test. Okay. I will tell you that the sample test I sent you, just a second. The sample test I sent you the other day, that one was actually a fairly hard exam. The average was 48% on that one. Okay. Yeah, I really expect it to be higher. I mean, we'll see. I'm just hoping that that'll happen. Because I was surprised in the last exam. Okay, so I want to look at the case where we have a resistor and a capacitor in a circuit. So let me draw the circuit. So I have a power supply. And I want to put a switch in my circuit. Okay, oops, I forgot to do one thing. Sorry. I'm not showing the power, it's not showing the PowerPoint. There we go. All right, sorry about that. So let me draw my circuit. I'm going to draw the circuit. I'm going to put a switch in the circuit. So there's my switch. And when the switch is like that, we say that the switch is open. Okay. Doesn't matter where I put the switch, whether I put it here or after the resistor and the capacitor like you see in the figure. Now, have you seen a circuit like this before? Actually, you have. If you remember, I did the demo with the flash bulb, with the 1 farad capacitor. That was an RC circuit. So I have the switch open. Okay, so I have the switch open, and then when I close the switch, meaning that I close the circuit. When I say close the switch, I mean the circuit becomes closed. So in other words, when I bring the switch to this position, now I have a closed circuit and current will go through the circuit. Okay. So let's leave it open for the time being and talk about this. When it is open, this is uncharged. Let's say this is uncharged initially. I is 0 initially. Okay. Then let's close this switch. So what's going to happen? Well, charge will flow through here. But we have a resistor. The resistor will oppose its current. So it's going to make, the resistor is going to make it harder for the charge to build up on the capacitor. Really what's going to happen is the resistor is going to slow down the rate in which the charge will build up on a capacitor. If there was no resistance in the circuit, the capacitor would charge up very fast. Okay, but now that resistor is there, so it's going to make it a little bit harder for the capacitor to charge up. It's going to Basically, it's going to take more time for the capacitor to charge up. Okay. Now, our rules for series and parallel don't work for this circuit, because I have a resistor and I have a capacitor. They're two different circuit elements. At least they're both linear elements, meaning that the voltage across them depends on linearly on some function, either the resistance or the capacitance. Okay. So what do? Well, I use Kirchhoff's laws. In fact, I'm going to use the voltage law. So what I'm going to do is set up an equation using Kirchhoff's voltage law. I'm going to assume the current is in this direction. And I'm going to assume the voltage drops in the same direction. So I'm going to assume the voltage drops in this direction. Okay? And I'll set up an equation. And then I'll proceed from there. So if I set up my equation, I'm going to get, if I go clockwise, I have a voltage gain. And since I'm summing in the direction of the current drops here. And then the current drops here. Any questions so far? Everything looks okay so far?
Can you go over how it dropped across the capacitor?
How it drops?
Yes.
Well, there's an electric field in between the plates, right?
Yes.
And if this becomes positively charged and this becomes negatively charged over this distance, doesn't the potential drop?
Okay, it is dropping with time.
Well, it's dropping with time, but let's freeze time for a moment, for an instant in time, though. Okay.
Okay.
Right. It still drops, right? Whether at that instant in time, there's still a voltage drop.
Mm-hmm.
Okay, because you have an electric field that points in this direction. You know that the electric field is in the direction of decreasing potential, right?
Yes.
So that means there has to be a drop here.
Mm-hmm.
Okay. So, and we can write it as Q over C because we know Q is C times V, right? Or C delta V, sorry. Right?
Yes.
Okay. So we're all okay with this equation? And what's nice is Kirchhoff's law works in any kind of circuit. You know, the rules for series and parallel are kind of limited. Because I can't use that here because I have two different elements. I can use this for any kind of circuit pretty much. Well, I can use it for any kind of circuit. I better be more specific, okay? All right, so I'm going to erase this. I'm going to erase my circuit real quick because I got to do some math. Not a lot of math, but some math. Now, how is I related to Q?
It's the derivative of Q with respect to time.
Okay, so I can write, oops. Right? And let's see, I'm going to multiply both sides by C. And let me isolate this term. Does this look okay? What kind of equation is that? I want to find Q. What is this called?
Differential.
Yeah, this is a differential
It's
equation.
separable.
It's a first order one, right?
Yeah.
And you don't have to have Math 33 to be able to solve this. We can all solve this because you've gone through Calc 1 and you've gone through Calc 2. This is something we can all solve. Because it's called a separable differential equation, because I can put all the q's on one side of the equation and all the dt's on the other side of the equation. And that's what I'm going to do. So I'm going to do this and say, okay, dq over c delta v minus q equals dt over rc. We okay with that? So Michaela, your question is, what are we solving for? We're solving for q. We'll get I from q though.
Oh, okay. Thank you.
Okay. So what's my next step?
Integrate both sides.
I'm going to integrate both sides. So I want to do it this way. I'm going to put limits in my integral, because otherwise I'm going to have to find a constant of integration. It's a little bit more work, but I can do it that way too. So let me just put limits. I want to integrate from the time in which we started, where this thing had no charge, to some final charge, q sub f. And so I'm going to integrate from t equals 0 to some t final. Is that okay? And then I don't like working on this board as much. I want to work on this board. When I integrate that, what do I get? I get natural log. Like I get a minus sign that comes out of it. Natural log is c delta v minus q from 0 to q final. All right, c delta v is a constant. And we'll talk about what c delta v means. This is going to be equal to t final over rc. We okay so far? You guys okay? I'm going to move this minus sign to the other side. Is that okay?
Go for it.
Yeah.
Okay, good. Oops, I just wrote on my wall. Okay. Let me put in the limits. And if you don't mind, I'm going to skip a step, and if something bothers you, let me know. Does that look okay?
Yeah.
Okay, so in reality, though, what does C delta V represent?
Q.
It's a Q, right? But what Q? What Q are we talking about?
The magnitude of the charge on the capacitor when it's fully charged.
Yeah, it's the maximum charge, right?
Yeah.
So C delta V is the maximum charge. So we're going to say let C delta V equals Q max. So let me write that in. So if this is the maximum charge, then do I need absolute value signs there? I'm doing a physical argument, not a mathematical argument here. Do I need the absolute value sign if I know that this is always going to be bigger than this?
No.
No, so let's get rid of them. Right, I'm using a physical argument. I can't do that in math class. What's my next step?
Wait, isn't QF equivalent to Qmax? Or is QF just like,
It's at some
that's with respect to time?
well, it's at some intermediate time. It doesn't have to be at the final time.
Oh, okay.
Okay, it can be any time. And I'm going to get rid of these subscripts in a minute. So,
You're going to
I'm sorry?
exponentiate both sides?
I'm going to exponentiate both sides. Yeah, so I'm going to get and then I'll get Q max. Now I got to write down here. And let's solve for Q final. Q final ends up being Q max times 1 minus e to the minus t final over RC. This represents the charge on the capacitor at any time. So can I get rid of these subscripts and leave it like that? The reason why I put the subscript here is to make it look different from here. I could have put Q primes here as a dummy variable, but that's okay. So this is the charge on the capacitor as a function of time. Now, when is this a maximum value?
When t is going to infinity.
Yeah, when t goes infinity, this is maximized. Okay. So Q equal Q max at t equals infinity.
That's not like practically true though, right? Like it happens in a finite amount of time.
Pretty much. I mean, pretty much. There's little details we're ignoring, but yeah, in principle, it's not going to take an infinite amount of. I mean, in reality, it's not going to take an infinite amount of time.
Okay.
Okay. All right. So this is the equation for charging the capacitor, the Q. But once we know this expression, you pretty much know everything else, because I can write the voltage across the capacitor as a function of time, because the voltage across the capacitor is this divided by C. And this is the battery voltage or the power supply voltage. And I can get the current. The current's a derivative of this, right? I is dq over dt, which is going to be Q max over RC e to the minus t over RC, which is delta V over R. And what's delta V over R?
Current. Or
Right,
is
it's
it
the
1 over
current. When though?
The
At
maximum
t equals
current?
0.
At t equals 0. And is this the maximum or minimum current?
Max?
The maximum.
Okay. That's a C, sorry. You guys can see far down. I can't see the camera very well. Hold on. That shows up okay, right? It's a little bit blurry. Or no, I'm sorry.
Like, I can't read it, but I know what it's supposed to say.
Okay. You had a question about leaving the subscript? I'm leaving this subscript because I know that's Q max. If that's your question. Okay, yeah, this, I'm sorry, I missed the previous question, but this is an actual, that one's not arbitrary. Okay, so we have a bunch of equations. Let me rewrite them over here because I'm running out of space. and you can probably see them better. Okay, you can see those better now, right?
Yes.
Okay. Now, a lot of times we use a substitution for this. Now, this actually has units of seconds. How do I show that? R times C has units of seconds. Well, the units for R is volts per amp. The units for C is coulomb per volt, which gives me a coulomb per amp. But an amp is a coulomb per second. So the units of RC is in seconds. And so a lot of times we define the letter tau to be RC and call it the time constant. So the Greek letter tau denotes the time constant, which is characteristic for the RC combination, which I got rid of. Let me draw the circuit again. So a lot of times we can write this not in terms of R and C, but in terms of tau. Does that make sense? It's just a definition. So what does this mean? Well, after one time constant, what's the charge on the capacitor? We can ask that question. If we define this, then we can write Q equals Q max times 1 minus e to the minus t over tau. And we can say, what is Q after 1 tau has elapsed? Well, then I do the following. Tau over tau. And what's e to the minus 1? Well, it's about 0.37. And so this ends up being 0.63 Q max. So after one time constant, the capacitor is charged at 63% of its maximum value. After two time constants, the capacitor is charged to 86% of its maximum value. Okay? So let me introduce a couple of terms here. What happens to the capacitor? It charges up, right? And the current varies with time. The voltage varies with time. So you apply power to the circuit responds where the charge builds up. After a long period of time has elapsed, what happens? The capacitor is fully charged. All the energy it can get is stored in there. You can't put any more energy into the capacitor. The system reaches steady state. Okay? So at t equals infinity, okay, capacitor fully charged, and we say that the system has reached steady state. There's no more energy going into this thing. The energy in the capacitor stays constant. Okay, and I want to mention this term because this term is used a lot. If those of you who have taken 215, you probably had Harris tell you use this term a lot too, right? Talk about steady state. What about the time before you reach steady state? What do we call that time?
Transient.
Yeah, we call that the transient time. Okay, so the time in which the capacitor is charging, we say that the capacitor is responding to the power supply. This is called a transient response to the power supply.
In my DE class, when we talked very briefly about circuits and stuff, and maybe you can connect my misunderstanding, but I thought the transient solution meant one that kind of like pitters out to zero over time.
It does, right? And well, I mean, the current does.
Oh yeah, I guess you're right. Okay.
Yeah,
Thanks.
the current goes to zero over time. But Q stays static.
Right, and that's why it's the steady state solution.
Yeah, I mean, so whether it stays static or it goes to zero at the same, I mean, they don't change anymore, right? There's no more energy
Right.
going into this thing.
Yeah, okay.
Okay. And we're going to encounter this again when we do this circuit, but the power supply is an AC power supply. We'll have another element in there too, and you'll do a very long lab on it, okay, at the end of the semester. And the mathematical solution to that problem is exactly the same as the mathematical solution to one of the problems you do in physics 215. It involves the mass on a spring.
Wait, so I have a couple questions. So for each problem we do of these, do we have to derive an equation? Like, is the equation going to change?
No, you don't. The only thing that's going to change is this. Only the R and the C are going to change.
Oh, okay, so we can use this equation for every RC circuit?
Yeah, I don't expect you to derive it on the test. In the lab, there's a lab coming up called a Transient Response Lab. You're going to derive, no, you're actually not going to derive this. You're going to derive a version of this, okay? You should know how to derive it though, okay?
Wait,
Oh,
so
okay.
the current is the transient solution?
These expressions represent the transient solution. When t goes to infinity, nothing changes. That's steady state.
Oh, okay, yeah, we didn't do circuits when I took DE.
Yeah, so, okay, so since you folks are asking, when we do this problem with an AC power supply, and we have another element in here called an inductor, we're going to solve a second order. I'm going to solve it for you. Actually, I don't know if I have a video that's on YouTube and I'll refer you to it. I'm going to solve an inhomogeneous second order differential equation with constant coefficients. It's a mouthful. But I'm going to use the method of guessing. I'm going to guess a solution and come up with the answer.
Sounds very physicist of us.
Yeah. Well, because I can't do it the formal way, right? Because it's Math 33 is not a...
Right,
Yeah.
I was just
But it
being-
works. I mean, it works. I mean, I'm just using physical intuition. But you get two solutions. You get a steady state solution, and you get a solution that varies with time, the transient one. The steady state solution, basically the current, the maximum current stays the same. I is not going to be constant, but its amplitude, its maximum value will stay the same.
So I was also wondering, while the capacitor is charging up, like when it hasn't reached its full capacity yet, is there a current past the capacitor, like leading to the negative end of the battery?
Yeah, that's so. Yeah, people ask, what the heck's happening in between here, right? That's your question, right?
Yeah, well, I was just wondering if it's like if you had a hose that was going into a bucket, like none of the water is going out of the bucket until the bucket fills up. Is it like that, or is it different?
Yeah, capacitor is kind of, I can't think of an analog for a mechanical analog to a capacitor, really. What's happening is the plates are the charge on the plates is changing. There's nothing going through there. There's no physical charge. Now we got to be careful though. If we have a dielectric, there's charge moving in the dielectric, right? But it's not jumping from one part of the circuit to the next. You see what I mean? Charge is changing here. Charge is changing here. So dq dt is changing. So you have a dq dt here and a dq dt here, but there's nothing jumping across the gap.
So does that mean there's no current like to the right of it? Like past
You mean over
the,
here? There's current everywhere except in between here.
Oh, so there's current on both sides. It's not just on
There's
one
not
side?
inside. However, there is charge moving in here, but it's not jumping from one side of the circuit to the next. It's not going from if there's a dielectric here. If this was a vacuum, there's nothing happening over here. That's probably the best way to look at it. There's nothing happening here. What's happening is on the plates. The charge is changing on the plates.
Yeah, I just mean like past the plate, like past the plate, to the right.
In this region, right?
Past the rightmost plate.
Oh,
yeah,
here?
Yeah, past the rightmost
Oh,
plate.
so that's over here. Yeah, there's charge moving here. There's charge moving here.
Okay, so that's
and
the
there's
negative
moving
charge.
here. I'm sorry?
So that's the negative charge moving to the right side of the plate.
Yeah. Negative charge is getting here, and when negative charge moves here, then positive charge gets here because the electrons are going to go back, are going to go this way.
Oh, okay.
Okay?
Thanks.
But there's nothing moving in between them. And again, if you put a dielectric in, there's charge moving in the dielectric, but it's not jumping from the dielectric to the capacitor plate. Okay? That one's a hard one, and the capacitor problem is going to cause issues later on in this course. You'll see what I mean. Okay. Okay, so I just want to make sure you've seen all the terms: time constant, steady state, and transient. Okay, let me write the word transient. These are called a transient response.
Professor?
Yeah.
So in the formula, the R is the equivalent resistance of the whole circuit, right?
Yeah, if I have multiple resistors here, this would be the equivalent resistance.
Mm-hmm.
Okay. What does the graph look like, maybe, of the charge as a function of time?
Does it start at the magnitude of like the potential difference, and then it just like goes down exponentially to zero, like off at infinity?
You're talking about the current?
Oh yeah, I guess I am, huh? I don't know then.
Yeah,
Just the opposite of it.
let me get to these equations that you see here. In the slide I've already derived, so let me go through these. Let me go past these slides. I have two graphs. Okay. Yeah, one thing I forgot to mention when you look at the equation for the current, which I have on the board. Let me go back to the board real quick. I kind of jumped ahead of myself. I'm sorry. But if you, after one time constant, you have e to the minus 1, the current is 37% of its original value. Okay, let me... And of course, you can use Ohm's law to find the voltage across the resistor. Current times resistance will give you the voltage across the resistor. So here's a graph of the charge on the capacitor as a function of time. It increases exponentially after one time constant. That first horizontal orange line that you see in that graph is basically after one time constant. The capacitor is charged to 63% of its maximum value. And after a long period of time, the capacitor reaches Q max. And so this is the current in your circuit. And this is what you were saying, Damien. All right, it starts off at some maximum value, t equals 0. And it goes to 0 at t equals infinity. Now let's say something. Let's talk about this real quick, okay? How is the capacitor behaving at t equals 0? These are things you need to know. How does the capacitor behave at t equals 0?
Is it just like a wire?
Yeah, so at t equals 0, the capacitor acts like a wire. When it's charging. Okay, when it's charging, at t equals 0, it acts like a wire because you get maximum current because the current in here is just V over R. But what about t equals infinity?
It's like an open circuit, right? It's like a switch.
Yeah, that's right. At t equals infinity, after the capacitor is fully charged, it acts like an open circuit. So capacitors, one of the reasons you use capacitors is to block DC signal from your circuit. There might be an application where you want to block DC from your circuit and allow AC to get through. Okay, so that's one of the applications. So and once you reach steady state, the capacitor will block DC current.
Does having a dielectric there increase the amount of time or decrease the amount of time it takes to become fully charged?
Well, that's going to increase C though, right? So it'll increase the time. It'll make your time constant bigger.
I see. Okay.
So what you want is, if you want to block DC and let AC through, you probably want this to be fairly small. Of course, it depends on the application, right? All right. So let me write the last thing down. Okay. All right, so pretty much all the terminology I think I got all the terminology down because that's one of the things students forget is the terminology, and I wanted to make sure I went over that. So let's talk a little bit about energy in this circuit. Okay. First of all, what is the energy in the capacitor? If you look at the energy stored in the capacitor, it's going to depend on this thing squared, right? Which means that
you could do the charge squared too, right?
Yeah, you can do either one, right? It's going to depend on, so it's going to have a e to the, so when you square it, then you'll have a 2 in the exponent there, right?
Yeah.
Okay. All right, so I'm going to leave those equations there. Let's talk about the energy when you charge a capacitor. What does the battery do?
Creates a potential difference between everywhere in the circuit.
So when uh-oh. When capacitor is fully charged, the battery, or the power supply, whatever you want to call it, for our discussion, it doesn't matter whether we're talking about a battery or a power supply, delivers this much energy. Oops. That's how much energy is delivered by the battery. The battery, the voltage across the battery never changes, and it delivers this much charge. So the total work it does is Q delta V. Are you okay with that? That's the energy delivered by the battery. You can write it as C times delta V squared because Q is C delta V. Does that make sense?
Can you explain that again?
Well,
Can you explain that again?
okay, so the battery voltage stays constant, correct?
Yeah, what is Q delta V? Is it just,
The energy.
is that supposed to be,
Joules per coulomb
Okay.
times coulomb.
right?
Right, because this is constant. This is always constant, right? In a capacitor, this is not constant.
Yeah, yeah.
Okay, so that's why I can just multiply them together. My final Q times my delta V is how much energy is delivered by the battery. But that's not the energy stored in the capacitor. How much energy is stored in the capacitor?
Q squared over 2C.
Yeah, so I'm going to write in terms of this. It's going to be either 1/2 Q delta V or 1/2 C delta V squared. Only half of it is stored in the capacitor. Where does the other half go?
Is it the resistor?
Yeah, so let's see, let's prove that, right? Oh, by the way, how can I derive this? I mean, granted, we know this already, right? But if I wanted to derive it, how do I do it? Well, that's going to be kind of hard.
Are you talking about like when you integrated the potential energy term, or like the
Yeah, I'd have to do the
voltage?
potential energy term, but I'd rather do it the way I did it earlier, right? Instead of doing it with these complicated formulas. It's better to do it the way I did it early in chapter 26. Now let's do the battery, the resistor. What do resistors do? They dissipate energy. They take energy out of the system. Well, what's the power? Well, it's delta V times I. Actually, let me that's delta V of the resistor times I. Or I can write it as I squared times R. And I'm going to write it this way. It's easier. Well, so what's the energy lost by the resistor? It's going to be this thing squared times R, which is going to be I max squared times R e to the minus t over RC. So how do I figure out how much energy is lost from this? What do I do? How do I get from this to energy?
Do you integrate it?
Yeah. For lack of a better symbol, I'm just going to write down energy loss. It's going to be the
Is
integral.
power?
I'm
Is
sorry?
power joules per second? Is that what a watt is? Is a joule per second?
Yeah, joule per second, right? The same as, you know, when you
Okay.
learn in 205, you learned it, right, as power. And this
Yeah, I
this
just
thing.
couldn't remember the units. Thank you.
Oh, okay. But I want you to remember you're gonna see different forms of this equation. I didn't mean anything, but I'm just trying to say you're gonna see different forms of this equation in 205 and in 210 and in 215.
Right.
Okay, so you're gonna see it a lot actually. Okay, so I'm gonna integrate this thing. Oh wait, I screwed up. What did I screw up at? Up here.
You did 2t in the numerator.
Thank you. Okay. What are my limits?
0 to t final.
0 to what? I'm sorry.
To t final.
Yeah, so when the capacitor is fully charged, what's T final?
Infinity.
Infinity. Let's make it easier. All right, I'm going to make life easier because otherwise if I put T final, it's going to be more work for me. Okay, now I got to integrate this thing. Let's see. Is this a hard integral? Yeah, that's not too bad, right? See, when I integrate this, please check my math because I screw up a lot. I'm going to get a RC over 2. I'm going to get a minus sign, I think. Does this look okay?
Yeah.
Okay. What does this come out? So when I put the limits in, what do I get?
Just a 1, right? Or a -1?
A -1, and that's going to cancel with that. Let's see. So what's I max again? It's delta V over R. Well, it worked out. Okay, I didn't screw up. That's good. So it worked out. So half the energy is lost. I always worry I'm going to screw up that integral. Do you remember doing the problem in chapter 27 with the capacitor and the resistor? I hope. There was a problem where you had, I can't remember. And it asks you to calculate the energy before and after. And I think it ended up being half what you had after than before. That's because of this. It's always a half. Half the energy is lost in the wires. Even if you got rid of the resistor and you just put wires in there, half the energy would be lost by the wires.
Why?
Because the wires are taking, I mean, the wires are not ideal, right? They're really not, they do have an inherent resistance in them.
But why is it always a half? Because wouldn't that mean that they're all not ideal in the exact same way?
Yeah, it just works out that way. It's weird, right? Why is it always a half? It's hard to answer. It just is that way.
What do I Google to make this make sense?
Well, this part makes sense though, right?
Yeah, I get that part. That makes
Okay.
sense.
The fact that it's a half is what's bothersome, right? That it's always a half.
Yeah.
Yeah, it just works out that way. It's kind of like, I don't know. I mean, this is the way I see it because it bugs me too, right? Why is F equals ma? I mean, it just is that way, right?
Experimental results. Oh God.
Okay, right. It just
this.
is that way. Yeah, but this is derived though. That's what's weird.
Does it have something to do with the fact that we're integrating from 0 to infinity? Like the 1/2 is just always going to be the constant that pops out. But if we integrate it to like an actual time, then we would get a different constant out front than 1/2.
Right, but if you eventually you have to let that time go to infinity, though, right?
Well, right, yeah. In practicality, I mean, I have no clue.
And that's the thing. It just works out that way, and it's unsatisfying. But yeah, that's just what happens. I mean, granted, the capacitor reaches its maximum charge, probably not an infinite amount of time. There's probably effects we're not considering. Okay, I mean, there's always energy lost to the surroundings. There's always energy lost to the surroundings. We're ignoring. And what we'll find out later on this semester is that, I'm going to ask the question, where is the energy coming from in the capacitor? This is even mind blowing. Okay, this is more mind blowing. So, if you were to consider the flow of energy in the capacitor, which way is it flowing? Of course,
Well, that doesn't make sense because it's not. Or wait, never mind. I don't.
I mean, there's energy going in here, right? You can talk about the flow of energy.
Is it the same direction as the potential difference?
Yeah, you would think that, right? But that's not. We'll cover it in chapter 34. That's not the case. It's very bizarre, and that really bugs me. It's actually this way. The flow of energy is perpendicular to the plane of the capacitor plates, and in this direction. Actually, not perpendicular, parallel to the capacitor plates. Sorry.
Does this have something to do with the fact that when you put in a dielectric, it is accelerated inwards?
No, it has to do with the electromagnetic waves. It has to do with the fact that the electric field in between the plates is time variant. That's what it has to do. Mm-hmm. It's very bizarre, right? You would never think the energy goes this way, but it does. But we'll cover that later. You don't have to know that for this test. You will for the last test. Okay. So we've pretty much covered everything regarding the capacitor, all the details. Well, when a capacitor is charging. What about when it's discharging? And I'm not going to go through the math for the discharging capacitor. It's in your notes. But what happens if I look at that picture? Let me make that picture bigger. Okay, finally got it to work. Okay, so now let me make that picture bigger. I have a capacitor. I charge it up. So switch S1 is closed. Capacitor is fully charged. Then I open S1 and close S2. I don't know why I have two resistors in that circuit. That's my bad, but So I have a fully charged capacitor. And I really should have only one resistor. That's my bad. What's going to happen when I close S2? This is charged, and I have a resistor here. This is the demo I did with the 1 farad capacitor and that flashlight, that flash bulb.
Isn't all the current going to go towards S2 or towards the second resistor?
Yeah, it's going to go this way, right? It's going to start to discharge. And I can derive an equation for the charge as a function of time and the current as a function of time. I use KVL again. Some of the voltage drops. So if I go around this loop, okay, the current's going to go, let me use a different color. Current's going to go like this, and then some of the voltage drops in the same direction. And I'll say, okay, the voltage drops for the resistors I times R. And then if I go around this way, then I have a voltage gain. Now, the question is, how is I related to Q now? Yeah, Chase, it's almost like a temporary battery. It's a little bit different though, because the charge is changing on the battery acts like a pump. This one is actually the charge is, the plates are losing energy, they're losing charge. So what's the relationship between I and Q?
Is it negative dq dt?
Yeah, perfect. It's got to be minus because the plates are losing charge. So then up here, I got to write that. That's a very subtle thing. So now, solve for Q. Q. And what you'll get is the following. Okay? And then I, which is minus dq dt, is going to be well, Q max is usually delta V is C delta V. So I will say this, sometimes books will put a minus sign in front of here just to say that the capacitor is discharging, but then that's inconsistent with this equation. So for years I was doing it that way, but I based on, and really I changed this last night, writing it this way is actually much better. We know it's discharging, but some books will actually put a minus sign here just so you know that this means it's discharging. Okay.
That equation for Q is the equation for the charge on the capacitor, right? And that's why it goes to 0. It's not the whole charge of the system.
Yeah, you're right. It's the charge on the capacitor.
Okay, thank you.
And it goes to 0. So in your notes, I derive it, but I mean, I didn't want to spend time deriving it because it's the almost the same differential equation. It's actually easier. So you should be able to go through this one pretty easily. Okay, see, in my original notes, I have a minus sign there, and I'm going to actually get rid of that because really your I is minus dq dt. And I think, if I remember correctly, our book writes it this way, and I don't like it this way. So, and really, we don't worry about the minus sign when we solve problems anyway, so. So after one time constant, the capacitor is charged at 37% of its maximum value. So one last thing I want to do is this fun problem. This problem, really I got this problem from a book. It's a really nice problem because everything you want to know about the RC circuits is in this problem pretty much. So I want to finish with this problem. So maybe it might take me a full 20 minutes. I wish it didn't, but it'll probably take me a full 20 minutes to finish. But I can use time to, if you want me to ask you some conceptual questions, I can do that, okay? So first question is, what is the current through each resistor at t equals 0? I close the switch. What is the current through each resistor? How does the capacitor behave?
Like an open wire.
Like a wire. Okay. So the capacitor acts like a wire at t equals 0. Okay, so I'm going to draw with the switch closed, so you can't, it almost acts like you can't see it, okay? And I got to save space, so I'm going to make things a little bit more compacted. And if you can't see something, just let me know.
But I thought a capacitor acted like a wire, like after it was fully charged, like t equals infinity.
No, because when this is fully charged, the current's 0, right? Put infinity in this exponent.
Yeah, but like, is the current like on either side of the capacitor?
Yeah, but there's no charge going on the plates or leaving the plates at t equals infinity. Isn't that true? When it's fully charged.
Yeah.
So it's acting like this then.
Oh, so when you said it acts like an open circuit, you mean like there's not consistency there? Like the wire's broken?
Yeah, that's what open circuit means. Open circuit
okay.
means you have an open circuit. It means you don't have right, to have current, you need a closed loop, right?
Yeah.
You need the path for the electrons to go through. When the path is open like that, the electrons get to the end here and says, where do I go?
Okay,
They can't go anywhere. But at t equals 0, the capacitor acts like a wire. Okay, so at t equals 0, it acts like a wire. So this one and this one are in parallel. Oh, okay. Okay, 1 over 15 plus 1 over 3. Common denominator is 15. Okay, check my math.
Wait, I'm sorry. How are they in parallel if there's a capacitor there? Is that not interfering with that?
What is T?
Equals 0.
So how does this behave?
Never mind.
Okay.
I see.
All
Okay.
right. You're right. After T equals 0, I can't do that. And what about T equals infinity? Then I have to draw as an open circuit. So yeah. So maybe I should say this. Maybe to be clear. Is that okay? Is that better? Maybe.
Yeah, because then I won't forget it in like 3 minutes.
Okay. All right. That's fine. So yeah, I should label it. That's my bad. What's 15 over 6? 2.5?
Yeah.
Okay. So how many volts was that again? 9 volts. So then the current through this one is 9 over 14.5 kiloohms. Let me know if that's too small. And I think that comes out to 600 microamps. Hold on. 621 microamps. Okay, so I have 621 microamps here. And I have 621 microamps here. What's the voltage across that one? Voltage times current. Let me check to make sure I did the math correctly. Okay. This one's 7.44 volts. What's the voltage across this one?
Is it just like 1 point something 6?
Yeah, 1.55. I guess I should have done it that way. That would have been faster. You're right.
If we didn't, oh, sorry.
I'm going to cheat here. So they add up to 9, okay?
Hey, Professor.
Yeah.
If we were to separate the two resistors in parallel back into, two resistors in parallel, the current across them would not be the same, right?
For these two, you mean?
Yeah.
Yeah. So I'm gonna go through and get these values now.
Oh, okay. Sorry.
Right? Because I know the voltage, right?
Right. Okay.
So I'm gonna take
and
this.
that's constant across them.
So I'm gonna take this divided by 15K.
Right.
Well, let me write the voltages down. Can you see that okay? Green, I know
Yeah.
green is not the best color. All right, so 621. So 1.55 over 15. 104 microamps. And this one comes out to be 517 microamps. 1.55 divided by 3. There's some round off stuff there, okay? So I know everything right now, right? This is at T equals 0. How do we determine Q as a function of time? That's part B. What do I have to do?
The voltage law.
What is it? Yeah, the voltage law. So you would have to apply Kirchhoff's voltage law and the current law, because you can say, oh, this is I1 plus I2. This is I1. That's I2. And then apply the voltage law. And then set up your equations. I'm not going to do that here. And it turns out, you folks have the math tools to be able to do that. You're going to get a system of two equations and two unknowns. Okay, you will get two equations and two unknowns. It's just that each equation is a differential equation. Well, actually, if I use this loop, it won't be. This will not be a differential equation. Okay. But this loop will give me a differential equation. So you have two equations, two unknowns. At least one is a differential equation. You solve for one of the variables and then integrate. And that's it. So you will be doing a problem like that when we get to chapter 31. There's a homework problem where you're going to work not with capacitors but inductors, and you have to use Kirchhoff's laws and set up the differential equation and integrate. I'm not going to have you do it here yet. So that's what part B is. How do you determine Q as a function of time? Now, if this thing wasn't there, it would be really easy to do this problem. Why?
Because you'd only need one loop.
I mean, I can almost write the answer down. I can write the equation for current as a function of time like that if this resistor was not there. You know why? What's the voltage drop across this guy? If that's not there, what's the voltage drop across this guy? Let me draw the circuit without that resistor.
Is it just 1.5 times the current?
Well, that's the circuit, right?
Is it 9?
Without the resistor in it. So let's say that's not there. The total current delivered by the battery is going to be, the current through here is going to be 9 volts over, what is that resistance, 15 kilo ohms? Plus, the current through this loop is going to be that's it. 10 over 3,000. Where R is this resistor and C is this capacitor. That's how fast I can get the answer. Because I've asked that question on exams. If that resistor is not there, because the voltage drop here and the voltage drop here is the same. I have two circuits that are connected to a 9-volt power supply. So that's my total current. I can write it down like that. Of course, I have to start with, I have to know this equation ahead of time. But once I throw that resistor in here, like I do up there, then it becomes a real pain. Let's find a steady state current now. I'll put the time again. And so at t equals infinity, how does the circuit behave? That's an open circuit. So all I have, oh, it's really easy now. What's 15 plus 12? 27. Both resistors have 333 milliamps going through them. What's Q max for the capacitor? And I'm going to have to erase the board. What's Q max for the capacitor?
Is it the capacitance divided by the volt, or the capacitance times the voltage across it?
Yeah, so we want to know Q at t equals infinity, which is going to be C delta V sub C. So I need to know the voltage across this thing, right? And isn't it going to be the same as the voltage across this resistor? Because it's open circuit, right? Because my circuit looks like this.
So we determine this by looking at the circuit when t is equal to 0?
No, t equals infinity, right?
Well, right, but if you're... Oh, sorry, yeah, you said open circuit, my bad.
Yeah, so we want to look at this one, right? Because the voltage across this guy is going to be the same as the voltage across this guy. There's no current here, so there's no voltage drop across the 3 kilo ohm resistor. So if this is at 0 volts, this is at 0 volts, this is at 0 volts. I don't know what that is. Well, it's going to be the same as this point, which is the same as the voltage across this resistor. So I got to take 15 times 333. Oh, that's microamps, sorry. So the voltage across the capacitor is going to be 15 kilo ohms times 333 microamps. It comes out to 5 volts. And so Q then is going to be 10 microfarads times 5 volts, and it's Q max. 10 times 5 is 50. 50 microcoulombs. Are we okay with that?
Can you go back to the part where you're talking about the why it's got the same voltage as the 15 kilo ohm resistor?
Because, well, over here, isn't this potential the same as this potential?
Yeah, because they're in parallel.
They're parallel, right? So if this is 5 volts, this point is at 5 volts. This is 5, that's 0. So this voltage drop is 5 volts.
I see.
Okay. I'm just referencing this to ground, but I mean, I can make it whatever. But delta, I always reference one to ground because it's easy to do the math.
Right.
Last question is, what is the current, or two more, there's 2 more left, sorry. What is the current after S1 is opened? So now, I keep misplacing my eraser. I need more boards. So now I have this. What is the current when I open the switch like that? Basically, I have that circuit. So this is part E. Right? If I open the switch, I had that circuit where the capacitor is at 5 volts. So that's what I drew there. What's my total resistance?
18 kilo ohms.
Okay, can I redraw it then?
Yeah.
And so the capacitor is going to be discharging through the resistor like this. And one of the equations we had for the resistor is going to be, or for the capacitor is going to be this. Here it's the voltage across the capacitor, which is 5 volts. So I is going to be 5 over 18,000 e to the minus t over RC. Now R is 18. Let me just do it like, let me write it like this. Okay. Let's see if I have a value for that. And then this is 0.278. I'm sorry. 278 microamps. I don't want to write this whole number out, so this goes over there. When I open the switch, the capacitor had 50 microcoulombs. How long does it take for that charge to go down to 10 microcoulombs, to 1/5 its value? Well, for a discharging capacitor,
It's going to be the natural log of something.
yeah, so I write Q over Q max, which is 1/5. I don't even need to know the answer to what Q max is, right? Okay, let's see if you guys catch what I did here. How's that? Everybody okay with that?
Mhm.
Okay,
Yeah.
because usually I have people who don't like that. And so RC is this number. I'm running out of space. 10 times 10 to the minus 6 is 10 to the minus 5. And that comes out to 0.29 seconds. Okay. I wish I had more board space because otherwise right now it looks kind of messy. So, yeah, make sure you know how to go through that problem. This says everything you need to know about the capacitor problem, pretty much. In fact, it has everything on this unit in this problem. Right, because it has RC circuits, it has Kirchhoff's law, series parallel, everything. You guys have questions in general? Because I'm done with the unit.
I have a question about a past lecture, actually.
Okay.
I think it was last Tuesday. You were doing a demo with like a bunch of light bulbs and stuff.
Yeah.
You referred to something as the power rating. When you said power rating, were you referring to the light bulb's actual power, or like its priority in terms of like lighting up because it had the lowest like watts, so it would light up?
Well, all light bulbs are rated, right? There's a number stamped on them. Right? If you look at a light bulb, okay, now granted, the new bulbs are a little bit misleading because they're LEDs, but The incandescent one, they're stamped on it, let's say 100 watts. That's the amount of power that's used up when you put 120 volts across it.
Okay, I just remember you saying that the power is greater if the resistance is lower. And I think this was in series.
No, I said that, okay, the power is here. So this is the power equation, right?
Yes.
So you set this to 120. And so what you'll see is the bigger the power, the smaller the resistance of the bulb.
Well, I guess like I was thinking of it in the terms of the equation of P is equal to I squared times R. And since all the bulbs were in series, the I squared factor would be the same for all of them. And in that sense, P and R would be directly proportional to each other. And that's why I was confused. I thought the greater the R value, then the greater the power.
You're right about that. But you know, you're confusing two things. The power rating and the power that's used up by the bulb. The power rating of a bulb is always with respect to 120 volts. That's why I'm using this equation.
Okay, so with my example, they would have different voltage, but in this example, their voltage is the same.
Right. So I'm talking about an isolated light bulb. Okay. When you have a single light bulb, the stamp on it is assuming 120 volts across it.
Okay.
The stamp that's on it. So that means V is 120. When you put it in series with another one, the voltage is not going to be 120.
So if the voltage isn't predetermined for, let's say, like 3 light bulbs, then
They're in series.
yeah, and there's series, then would my thought process be correct?
Yeah.
Okay. And is the case different when it's parallel? When like 3 bulbs in parallel?
Well, then they all get 120 volts, right?
Yeah, so I was then like I was thinking I would use that formula. And
Right.
that you have a
That's
even
correct.
Like, yeah, even if their voltages weren't the same. Oh, well, I guess it would be the same because parallel. I forgot. All right. Yeah. Thank you.
Okay. So I forgot to do one thing. You guys don't mind? I forgot to do my demo. Okay. You guys mind if I do my demo? I'm going to unplug my microphone. I spent a long time setting this up and then I forgot about it. Okay, hold on a second. This is going to be problematic. My apologies. I should have shown this demo a while back, but I got carried away. Okay, so I have hooked up an RC circuit. The RC circuit's back here. This is the capacitor. There's actually 2 capacitors I put in parallel because I'm going to take one out so you can see the effect. Okay. And so, let me turn that off. So I hooked up, I can't demonstrate the RC circuit with a multimeter because very boring results because you just see a constant value. You cannot see the time dependence with a multimeter. However, with this device, it's called an oscilloscope. This is not the one in your kit. This is a better one. Unfortunately, there's a better one than one in your kit. We were only allowed to buy the one with only one of these. So sorry about that. But this allows you to look at voltage as a function of time. Okay. And so I have a signal generator hooked up to it. You're going to be using this. And I put in a signal that varies with time. So I'm going to actually turn this power on and turn it off all the time, because otherwise what I'm going to see is boring. So what you see there, and you can tell how bad the power supply is. The yellow is the power supply. What you see here is the voltage as a function of time. I'm turning the voltage on and off. And really, the voltage should be basically, that should be a straight line. This should be a straight line. And it's curved because of it's not a fancy power supply, okay? I think that one cost $30. So that's what you're going to be using later on this semester, unfortunately, but that's what we're stuck with. Okay, the orange one represents the voltage I am measuring across the capacitor as a function of time. Okay, actually I have two capacitors in parallel. You can't see, it's hard to see the second one, it's like right here. Okay. All right, so let's focus on the signals. So I'm going to change how fast this thing turns on and off. Because how fast the capacitor charges depends on the RC time constant. If I change the signal faster, the capacitor will not have as much time to charge up. And you'll see that the orange signal is much smaller now than it was before. Let me go back. Let's go one more. So now I made the signal, I put the signal back to its original frequency. It turns on and off at 100 times a second. And you see that the capacitor can charge up almost all the way to the max. I'm going to take one of the capacitors out of the circuit. Reducing the time constant. And now look, the capacitor is pretty much fully charged. I changed the RC time constant by making C smaller, and you see that the capacitor is basically completely charged because you're asymptotically reaching the power supply voltage. Okay. If I actually made the time constant bigger, then you would see the capacitor not charge up as much. You will be doing this lab later on this semester. And you're going to be using this signal generator. You'll be using a scope like this. The only difference is that you can only look at one signal at one time. So let me increase the frequency again, give you an idea of what happens if the signal changes very rapidly. Oops. You see the capacitor doesn't have enough time to charge up because I'm turning I'm switching between on and off too fast. Okay. This is a little bit blurry. So you'll be doing this experiment later on this semester when you learn how to use the scope. Okay. So the lab after DC circuit analysis, you're going to use your scope. Like I said, it basically looks like this, except that there's only one input on yours, mine is two. And the oscilloscope is probably the most important tool you probably learn as an electrical engineer. It's way more important than the voltmeter, the multimeter, because you can see things changing with time. Okay, so I just wanted to show that. Any other questions?
Like about this or about other things?
Anything. Yeah, I'm done. I'm just done talking, so.
Cool, yeah, I had a question about the homework. I don't know if you covered it this morning in the office hours because it was about the problem you were going over with Damien, number 5 on the homework.
Okay, let me switch cameras real quick.
Okay.
I don't have enough USB ports.
And then I'm specifically having trouble with the second part of number 5, but I know that like Chase in the comments just said that he needed help with number 5 too, so I don't want to not cover that part if other people need to.
Okay, so the one thing I had hold on a second. Yeah, the one thing I had mentioned regarding number 5 is it's hard to see from that picture. That's one of the reasons why I gave that problem, is because you really don't want to learn how to just focus on putting numbers into an equation or really understand what's going on in the circuit. So when you look at the 1 ohm and the 3 ohm resistor, how are they connected?
They are in series.
Okay, so let me, hold on, I gotta plug in my mic again. Okay, so they're in series. So let me see if I can redraw it. So that's a 4, that's 4 ohms, right?
Yep.
Okay, and isn't that 4 ohms in parallel with the other 4 ohms?
Yes.
Okay, so I can do something like this. I'm such a bad artist, so.
I just end up redrawing it with straight lines.
Yeah, that's what you want to do. How are these two connected?
Parallel.
In parallel.
So basically, I have this, right? So basically what I have is the following. Like that. And
Yep.
so that's 8, so overall I have 4 ohms. How much power would be dissipated if a constant 20 volt DC source with an internal resistance of 0.3 ohms were placed across A and B? So let's do this. This is 4 ohms, right? So we want to know how much power dissipated by the circuit, by the battery.
Can you denote where A and B are? Okay, and then the 0.3 you just put over there. Okay, I get it.
Yeah, I can put this here, or here, or here. It doesn't. I mean, that part doesn't really matter, I guess. I mean, really, if I want to be technically correct, I guess I can do this. And then I'll put that dotted box, that dotted line you'll see in the book.
Yes, sir.
Question? I heard a question.
Yeah, I was kind of looking at the picture when you explained the that transition from the circle to like the square in the first place? How do you know the 6 and the 2 are in parallel with the 4 and the 4?
So this is A, right? And this is B. And so let's say I put a power supply between these 2 points. That's what that means. All right, if I put a power supply between these 2 points, what would happen? Well, the current goes this way, splits this direction and this direction, right?
Oh, wait, okay, yeah, I can see it now by looking at it. Never mind. Thank you.
Sure. So are we okay with this? And then I would just, since I want the power dissipated by the system, then I would say P is delta V squared of the power supply over R. Whatever that comes up. Mine was 0.3. I think everybody's is different.
Okay, so I did that and I got it wrong. Yeah.
How much power? Okay, so that's for the circuit. I guess they're not clear about what they mean. So what I calculated is for the whole circuit. So maybe they want for this. So if they want it for this, of course, I don't show my work, unfortunately, on the problem. So if they want this, then I have to find this current, right? I have to find the current through here. So I is going to be 20 volts over 4.3 ohms. Then, if I can find my eraser, if I want to find the power dissipated by this one, then I'm going to take that current square it and multiply by this resistance. So that's probably they're asking for this, not the whole circuit.
Yeah, that's what I ended up doing.
Okay.
And you got it right?
I don't have.
Yeah, I got it right on mine. My numbers are slightly different, obviously, but I just did it again, and that's how it came out.
Okay, that makes sense. It's just confusing because the question does say how much power would be dissipated by this circuit. I don't know.
Yeah, it should say by the resistor. Because when you throw this in, then that's going to be confusing.
Well, when it says across A and B, I took that as not including the internal resistance.
I see.
So when I multiplied it out, like I got the current coming from the power supply, and then I just multiplied it by the resistance of the entire.
Okay.
circuit.
Yeah, and that's what they're looking for. It's just easy to. I guess it's just easy to see it the other way. That's the only issue. But both. It's a matter of which one we're supposed to solve for, but either way is correct, right? If I was answering for the whole circuit, this would have been correct. If I'm answering for this, then this is correct. That's what I mean. Yeah, I just got to read it carefully. But you're right.
Can you work through number 10?
Okay, because I saw
homework.
number 4 listed real quick.
Oh, okay.
Four will go real quick. Or maybe not. Oh, 10 is the long one, I think. No, 10 is not the long one. Okay. So I'm going to make myself available. Because I have my student hours from 4:30 to 6 tomorrow. I can go beyond that tomorrow, okay? I'll send you guys an email. Just so you know. Number 4. And tell me if you can't see something because my markers are dying. And I have 2 amps going this way. And two volts, 10 volts. Okay, so yeah, it is a Kirchhoff's law problem. However, when I look at this, I know the current through here, so I know that what's the voltage drop across this resistor?
6.
6 volts. Okay. Let's say, so we have a current that goes this way, which is 2 amps.
I think the arrow is pointing the other way.
Oops.
It's hard to see.
Yeah, especially with someone like me. Okay. All right, so let's choose a direction for the current here. Which way should I point? Which way should I point?
Left.
This way? Okay, so let's call this current I. Let's some voltages in this direction. Let's just find what I is before we go on to what's here, okay? If I sum voltage drops, this is 2 volts, so I'm going to say I went up 2 volts minus 2 ohms times I. I was going to put 2I, sorry. And this is the voltage drop of 6 volts. That's equal to 0. So I get minus 4 volts minus 2I equals 0. So I is minus 2. Oops. Right? Does this make sense?
Yeah.
So I was wrong with this direction, right? Because I chose that direction, I got a negative sign for my current. That means my current is really to the right. Right?
Yes.
So I have 2 amps going this way, 2 amps going this way. What's going out this way?
So wouldn't the voltage there be 2?
2 amps this way. Well, it's asking for the current, right?
I was talking about the 1 ohm resistor,
Yeah, what's going through that 1 ohm resistor?
2 amps.
But you have 2 amps coming here and 2 amps coming here. How much goes out this direction?
4?
4. All right, if you have water flowing through this pipe and water flowing through this pipe, you're going to get twice as much going through here, right? If these two are equal, then the amount of water going through here is double either one of these two. Right? You don't sound convinced.
You did it a different way, kind of in your last lecture. You kind of pieced apart, like you took the 2 branches, or I guess you can call that, I guess, and you kind of summed them up to 0.
Okay, but I did that for one of the branches, right?
Yeah.
Why did I not do the same way I did the last time?
That's what I'm trying to figure out right now.
Well, look at this branch, right? How many currents are in here? Are in this branch? How many independent ones?
1
Aren't there 2?
in the first one.
Yeah, this one right here. How many independent eyes?
Oh, and 2.
Yeah, this one and this one, right?
Yes.
So I know this one, right?
Yes.
So I have one unknown
Yes.
and I have one loop. That's all I need, right?
I guess so.
Okay, that's what I did. So don't get into if you don't get into a formulaic way of doing all the problems. I mean, just be careful, because if I have enough information in one loop, then that's all I need to do.
Okay.
You could have done it your way, and it would have worked. You just got to not make a mistake. It's easy to make an algebra error if I set up 2 equations and 2 unknowns, and then start going through the algebra. As you do more problems, you will develop the intuition to say, oh, I have 2 unknowns here. I mean, 2 independent currents, but I know one of them, so I only need one loop to figure out this current. Then once I know that, then I can use the current law to figure out this current. Isn't this less work than what you would be doing?
Yeah.
Yeah. Is yours what you did wrong? No. The way you did it is correct. You can sum loops here, this one, and then use KCL, and that would be fun. It's still fine. It just takes longer. And maybe as practice, you can try to do it both ways. You should get the same answer. Right? That's a way to practice, is to see if you can get the same answer 2 different ways. Then you understand the material better. I know it's time consuming. Right? It is time consuming trying to do things 2 different ways, but a lot of times it helps you to learn the material. I remember taking physics a long time ago, and one of the things I would try to do is see if I can approach a problem a different way, because then I feel I understand the material better.
Could you tell me if this thought process was correct? I think this is the one I originally used. I couldn't remember, but since the top branch had 6 volts, and they're in parallel with the bottom one, I said the bottom one had 6 volts, and since there's already 2 volts from that.
Wait, where's the 6 volts? There's 6 volts across here, you mean?
Yeah, because it's in parallel with the top, which we found has 6 volts.
Okay.
And I think I said, since there's already 2 volts in the bottom, then that means we need 4 volts. So, and since there's a 2 ohm resistor to its left, then the current going through that would have to be 2 amps.
Actually, what you just said is actually faster. Here's what you said, right? This is 6 volts, right?
Yeah.
Then this has to be 4 volts, right?
Yeah, that's the way I was.
Okay, so that's 4 amps. That's even better.
Wait. Could you repeat that one?
Right. You said this is 6 volts, right?
Yeah.
So this has to be 4 volts.
Uh-huh.
4 divided by 1 is 4.
Oh, okay.
That's even better.
Yeah, I kind of got it off like a lucky guess, to be honest.
Right? That's even better. I mean, your thought process was better than what I did. So you have 3 ways you can do this problem. Right? I mean, the way you did it, I didn't even use a calculator. I mean, I didn't even have to write anything down. So that was good. Because you recognize if this is 6 volts, this has to be 6 volts. That's got to be 4 volts. That means 4 amps.
If we're done with this one, actually, could I ask a question? And it refers to the one I was asking about earlier, because I just wanted to like ask for one more just to make sure I'm thinking of it correctly.
Okay.
Wait, but first is the person who asked this question, like, are they okay with like?
Yeah, this makes sense for me. Yeah.
Okay. Cool. So with the light bulb again, and I get why you use the P is equal to the V squared over R formula, but since the voltage for the light bulbs are predetermined and the watts are known, then using the P equals VI, then we can find that they have different currents, right? But that's the current that's required to light the bulb up.
To make it run at that power rating.
Yes, so that's why I was confused at first and I was thinking about it. And so since like they all have the same current, and I'm guessing the current wasn't as high and it didn't like make it to that power rating for the other 2 bulbs, and that's why the one with the lowest like watts lit up. Is that why?
Yeah, all the bulbs. So we're talking about the bulbs in series. So
Yeah.
all the bulbs had the same current going through them. And so the one with the biggest resistance is going to have the biggest voltage drop across it. And that's going to be the one that's going to be dissipating the most power.
Okay. If we say like the current like increased through the loop, then would all of them light up?
How would you increase it? You would increase the voltage then?
Of the source?
Yeah, you have to increase the voltage of the source.
I feel like it would be compensated for somehow, but yeah, would that not change anything?
Well, if you're going to increase the current, you have to increase the voltage, right?
Yes.
Then if you increase the voltage sufficiently, then you'll get, what'll happen is as you increase the voltage, then the second bulb will light up and then the third bulb will light up. Hopefully the first one doesn't burn out.
Okay. So, because what I was thinking that the 25 watt one lit up because the current going through the circuit was just high enough to where it would hit its the power requirement, but it wasn't high enough for the other 2.
Yeah, you're reaching the power requirement for the 25 watt bulb as opposed to the other 2. You're not reaching that because the current's not high enough.
Okay. Just making sure I was thinking that correctly. Thank you.
Okay. Sure. Anything else? Oh, I have a question in here. I didn't see. So Jacob, the multimeter lab was due on the 9th. So if you show me when it was, you show me where I said it was due on the 11th. Show it to me. Because everybody turned it in on the 9th.
can you go through number 10?
Oh yeah, I'm sorry. I'm sorry. Let's see. All right, let me redraw this, number 10. Let me get a better marker. Okay, because my printout's small again, so. Okay. So this is reading 2 amps, right? So this reads 2 amps, correct?
Yeah.
Okay. So I want to know
Yeah.
this. I want to know this voltage, correct? But before I start just plugging equations in, let me write down. If there's 2 amps going through here, and 2 amps going through here, this is 8 volts, 8 volts. And then the voltage drop between this point and this point is 16 volts, right? Right, from here to here, it drops 16 volts. Does that make sense?
Yeah.
Okay. So that means from here to this drop and this drop are all the same because there's nothing here, right? Okay. And then there's the same current going through here. So let's say there's some current going this way. And I know this current. Can I just use the loop rule here to figure out what this value is? I mean, the voltage has to drop in that direction though, right? So maybe I should have the current going
Point the other way.
the other way. Let's do that. So this drop has to be 16 volts, right? From here to here, it's got to go minus 16 volts. Minus 6i, minus 24, minus 2i has to be minus 16, right? So actually the current's going that way. So I was correct originally. So I is 1 amp that way. So I have 2 amps going this way, 1 amp going this way. Then how much current goes this way?
One.
Okay. So I have 1 amp going through here. All right, I have 1 amp going this way. So what's the voltage drop in that direction?
Is it 12?
Yeah, but it drops, so it's minus 12 that way, or it drops in that direction, right?
Yes.
And it drops in this direction. So if I go in this direction, the voltage drops 12 volts, right? You go from 12 here, 12 here and another 4. So it drops this way by 16 volts, correct?
Yeah.
All right, it's got to drop this way by 16 volts though, right?
Yeah.
I'm trying to do this without really doing much math. So if it drops this way by 16 volts, it goes up this way by 16 volts, right? If the voltage drops by 16 this way, then it goes up 16 this way. Just do these two though, right? These two plus the power supply have to give me this voltage drop. So if it increases this way, delta V has to be 32 volts. This V has to be 32 volts. Wait, why is this 4? Why is this one 4? There's 1 amp going through here, so 4 times 1 is 4. Yeah, it's hard to see the decimal point, sorry. I thought it was 40 initially, then I took a closer look, it is 4. Is that okay? I did it without, doing loops, but if you want to do loops, you can. Right? If you want to do loops, you can say, okay, well, sum of the voltage drops equals 0. So if I go clockwise, I can say that's a gain, voltage gain minus 4 times 1. And then this is a voltage gain, 6 times 1. Voltage drop, voltage gain, and then a voltage drop. Should get the same thing. So I know this current is 1 amp, and I know this current is 1 amp, and I just use the loop rule. Or I can, and really I'm using the loop rule, but I'm kind of doing it in my head. I know this is a 16 volt drop. The voltage has got to drop by 16 volts this way, so this has to be 32 volts.
Professor, when you drew that blue curved line for, I guess, the flow of the current, is that like independent of what you wrote earlier with the
This one?
Yeah, is that like
I'm summing voltages in that direction.
Okay, so that's that doesn't have anything to do with the black lines from earlier.
No, these are the currents, right?
Yes, yeah.
And I'm not using another color just because my markers are dying. Sorry. I have an orange one, but orange is hard to see. I can try green. I think that's worse. I think that one made it worse. Is that okay for number 10?
Yeah. The tutor I was working with, we did it by the loops. It just seemed a little confusing. But we didn't solve for the current first.
Yeah, I mean, one of the things the first thing I would do is look at this loop. I have one unknown. I'd solve for one of the currents. So Chase, yeah, this is the same. There's no node here. I mean, there's no branching point. So the current here is 1 amp all the way around. Okay. The only way it would not be 1 amp is if it had a different path. But yeah, I mean, there's more than one way to do this problem. And I mean, the way I did it, I got this part 2 different ways. But in the end, I'm using Kirchhoff's voltage law. I always go back and forth about doing a problem the same way every single time. But then if I do that, then, and I don't show you a different way, I don't know if you develop an intuition for what's really going on in the circuit. Because I couldn't just sit there and just some loops, but it's hard to really see, to show you really the physics that's going on. That's why I kind of try to do the problems different ways. There's nothing wrong with, at least at the beginning for you guys to do the problem the same way. But if you see things, you might be able to do a little faster. Just like number 4. I mean, we saw 3 different ways to solve number 4. Anything else?
Why do you subtract the 24 in the bottom board?
Well, I'm going around this loop, right?
Yeah.
So isn't that a drop from positive to negative? Did I have it backwards in the picture? Is it backwards? Did I draw it backwards? No, it's okay. All right, this is, you go from high to low, right?
Oh yeah, my bad. Sorry.
Yeah. Does that work out what I did though? Hope I didn't screw it up.
Yeah, I got the right answer with that.
Okay. Yeah, but either way it's fine. I mean, when you take, those of you who take Engineering 17, a lot of stuff that you learn is based on Kirchhoff's laws. Actually, almost everything you do is based on Kirchhoff's laws in that class. You just learn shortcuts.
Why can't we learn those here?
Time.
Oh.
Time constraints. That's really the main issue. Like for example, when you have something with 2 power supplies, you could solve the circuit with, and it all depends on how fast the method is. You can do the following. You can solve this problem, take out this power supply, find all your currents. then do it again, put this power supply back and get rid of this, and then find all the currents here. And then the sum of the currents basically give you your answer. The sum of the currents in the two answers, in the two different problems you did. It's called superposition. So you can actually do this problem twice, one with the circuit in, and the other one with this there, but this one missing. And then your currents is just the sum of the answers in the two problems. And you learn that in engineering 17. There's a lot of techniques that you learn. We just don't have time for here. Ours is the most general. And there's a lot of videos online. They're not captioned. There's a lot of videos online on how to solve these problems. Okay. So I'm going to make myself available tomorrow at 4:30, and I can go beyond 6. Okay? I'm not sure who's left.
All right, that would be awesome.
Yeah, because it's the day before the exam, so there's quite a few left. I didn't realize there's 10 people left. Okay. That's awesome.
How many questions are going to be on the exam?
Well, there's going to be 5. Did I have 5? Yeah, 5 multiple choice questions and 4 problems. But the problems have multiple parts to them. But each part shouldn't. Of course, I'm saying it, but each part shouldn't take a long time. But that's me saying it. So. Anyway, but yeah, there's going to be, if you look at the homework, this homework set, there's some of the problems have many answers you got to fill in, but they go pretty quick. Especially the series parallel circuits, there's one with, I don't know how many answers you have to enter.
Yeah, number 13, number
Yeah.
14.
But they go fast though, right? Once you figure something out, the answers go bang, 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 right?
Yeah, I just haven't started on those. I've gone all the way up to 12.
Okay. That's good. You're almost done then. Yeah, get as far as you can today so you can use the time just to focus on getting ready tomorrow. You can ask questions. All right. I'm going to end it here then.
All right, thank you. See you tomorrow.
All right. See you.
How soon will this lecture be posted?
Well, the one on Canvas probably takes 1 or 2 hours, I think. Although this one right now is 2 hours long, so we'll see how long it takes. So look at Confer Zoom.
Yeah.
The one I'm going to upload on YouTube is going to take a long time because I'm over 2 hours right now on this. And so this video is going to be 20 gigabytes.
How long will the Confer Zoom one be?
A couple hours maybe.
Okay. Thank you.
All right, sure. Bye.